Okay, so Lucy is not going to be happy because we're actually going to look at that problem again. Because when I left the office, I was like, okay, something strange. And I think I just wasn't seeing something, and actually the problem is not difficult at all. So let's see, what was the problem? Well, I brought a lot of stuff, but I don't know if I brought that problem. So let's see. Yeah, I have yesterday's class notes still with me. Yeah, it's this one over here. Okay, so I think it's this problem over here. Okay. I think I saw here one handout. Yes. Okay, so guys, remember we're doing this problem yesterday, no? Mm-hmm. Okay. And basically, let me write on this page. Don't write that much. We ended up showing that all right, so we're gonna have, so we have the post over here that we need to design. This, which is here on the plane, okay, and basically yesterday, what we're showing is that if this was the Y, this was the X, and this was the Z, the propeller here is rotating about, is rotating on the around X, no? Mm-hmm. Okay, so that was creating a force on the Y direction and another force on the Z direction. Mm-hmm. Okay? And probably we say that this one was equal like something like little mass, I think capital M, what was the distance, little r, I think, no? And then whatever, sine omega t or cosine omega t. But basically, what we had a little discussion yesterday is that if we look here at the force F, all right, the magnitude of the force F, it would be acting, let's say, it doesn't matter which way you act, up or down, but let's say it would be acting down over here, Fy, okay, or up, doesn't matter, Fy. So this would be creating what at point A over here? This force is creating a moment about point A, no? Mm-hmm. And this is going to be deflecting, this part over here due to this moment will be deflecting something like this. Okay? So really from the force Fy, we are creating a bending moment where we have this equal to my over I, where I think we said that the value of the force would be what? Was it m omega square r? Then this was, I remember, like r sub outer divided by the I. Okay? I will redo this in a minute, but just want to clarify. Now, what would be the force Z doing? And that's what we had a little discussion, and I think it's because I didn't sketch it properly. What is the force D doing now?
It's also exerting a moment about point A.
But it's creating a moment about point A, but this time the moment will be about which axis?
X.
Will be about Y, no?
Yes. Oh, okay, you can model it as either.
Yeah, it will be rotating about this. So if this is a cross section that we are doing the design, actually the moment that is created is around this area over here, no? Mm-hmm. So this will create what? This will be torsion. Create torsion or shear, no? Mm-hmm. And the expression for shear here will be is T times R over J. So basically what we have is that the force Fy creates a bending moment, the force Fz induced or creates torsion, which would be the same as shear stress.
Can you move the paper?
Oh, sorry, will be shear stress.
Mhm.
So now I'm probably gonna have to repeat everything. Because she's the one that brought the issue, and then let's wait up a second for Lucy to get ready. Fine, and I try to maybe just re-explain this on a different piece of paper. Okay, so is Lucy ready? All right, so, not yet. Okay, so Lucy, we're saying yesterday when solving this problem, we had the propeller which is rotating about the axis y and z, no? So within that plane, y and z, we had that this was creating two forces, one on the y, one on the z, okay? The one on the y will be minus my squared r, and what will be the maximum amplitude? Well, omega will be equal to 90, no?
Mhm.
What will be the maximum amplitude for this one? Where cosine will be equal to 0. So what will be the magnitude of the force? In either case will be m omega squared r. All right? So this is the magnitude of the force. So we go back to this little figure. If we only look at the force Fy, all right? So only this force over here. What is this force creating? This force is lifting this end up, so it's creating a moment about point A. Correct? So what it's doing is making this to want to bend in that direction. Yeah? So it creates a bending moment. Now, and that's where we create the issue. What about the force S sub z over here? S sub z over here is creating a moment about what axis? About this section here. What would be this axis over here? So the force Lz over here is creating a moment about which axis? Sorry, this would be y. The force Lz will be creating a moment about this axis over here, no?
Mhm.
Okay? So now if we look here at the cross section, what type of loading would this be? Would that be bending or that would be shear?
Sure.
This is shear. So the force Fz creates shear, the force Fy creates bending. So both of them are not creating bending. So Fy is going to create bending, Fz is going to produce shear. Okay? So we go to yesterday's class notes, maybe we need to rewrite the last page. So I think we have this one for the bending. So if you want to just restart the problem if you want. Okay? So we have, this is the problem. Let me take a page here. So the example. So we're gonna have, again, this is our little unbalanced force, so I think this is M. I think this point they call that little distance here R. Okay, so I'm amplifying everything a lot. I get that distance here will be capital R. Really, they give us that distance, but I don't think we're going to need it. This is H. This is point A, where we need to calculate the stresses. And we know here we have a circular cross-section. All right? And we had over here, we look at the figure, we have the reference frame. This is X. This is y. So this would be z. And I remember what I did yesterday, probably I'm going to change the notation, I'm pretty sure. And this will be capital omega t. So, okay, so if you want, let's just redo everything from zero. How do you want to call this point here? This could be A, this could be B, this could be C. All right? So if we look at the unbalanced mass M, and we do letter 3-point diagram, so this will be C. This is M. Need to put a page behind. Yeah, too late. And this will be the distance letter R. This is capital omega t. And again, y, x, z. So we try to find out what are the forces acting over here. What do we have? Summation of forces equals to MA. And maybe let me give a name to this point over here as well. Let's say this would be O, whatever. Okay, so the mass is in which plane? It's on the y-z plane. So we could say that we have force on the y, force on the z plane. This is going to be equal to m times the acceleration of which point? The point where the mass is, no? So it should be point O. So we could calculate the acceleration of point O from where?
From point C?
From point C. So we have acceleration of C plus alpha cross R of O with respect to C minus, this would be the capital omega square R of O with respect to C. So this is basically the same thing we did during the derivation. So over here, what do we assume? Is that the propeller is rotating at
Constant angular velocity?
constant angular velocity, which is going to say what? That the acceleration is
0.
0. Now, here we're going to have 0, Fy, Fz equal to m. What do we know about the acceleration of C? It's going to be in what direction? It's going to be any acceleration about point C? Is it moving or is it fixed?
We can assume it's fixed.
We can assume it's fixed, correct. This is 0. So now we're going to have, this is going to be equal to what? Minus omega squared. What will be the position of O with respect to C? So the distance, so be careful here because yeah, what would be the x distance? Would be R, sorry, would be 0. No, would be,
Yeah, along the x-axis it would be 0.
and on this axis would be 0. Now what would it be? Now is where it gets difficult here. What would be about the y?
It would be r sine of omega t.
Sine of omega t. And about the y would be r of cosine omega t.
Mhm.
So basically from here we're going to get that the force Fy, which is the same thing as we got before, we go to what? Minus m omega squared r sine omega t, and f of z will be equal to minus m omega r cosine omega t. Okay? So now, when you do design of structure, generally you're always going to assume the worst case scenario, no? So what would be the worst case scenario? So the maximum loading is what? So for Fy, what is the expression?
M omega squared R.
Will be, m omega square r. We can say over here with letter r. Sorry, letter r. Could be plus or minus now, depending on the sign. But will this will correspond to what? When the sine omega t will be equal to what?
90 degrees.
So will be, let's say,
Which one is that?
90 or 180, no? Plus minus. Okay? Then what will be the worst case scenario for Fz? Omega t equal to what?
0 or 180.
Yeah, 0, 180. So here I did a mistake. This would be 270, no? And this should be equal to what? Plus minus m omega squared, again, letter r. Okay, so let's look at the two cases over here. So, case one, let's see at stress due to Fy. So if we do the figure, over here, this would be our point A. Fy can be up or down, okay, it doesn't matter. Let's say it's up, so plus minus Fy equal m omega square r. So this will be creating what? This is creating a bending moment this is creating a bending moment m that will be equal to what? F of y times r, and will produce this to bend in that direction. Okay? So the moment then will be equal to what? So letter m capital omega squared, letter r capital R. Notation becomes complicated. And this will be inducing what? Bending stress at A. So we know A is a circular. And if we look here at the figure without putting too many things. Okay, it doesn't matter, but what will be the stresses maximum?
On the outer rim, either to the full left or the full right.
Correct. So it would be MC over R, MC over I, where C should be equal to what? The outer rim. So that's too many. I can just use the diameter here, not use another R. So let's say this will be the outside diameter.
Divided by 2.
Over 2, no? Okay? So at the end, I, what was the expression for I think you told me was, so if we use the radius would be
Pi over 4.
pi over 4, but if we use the diameter would be,
Be,
so 2, pi over 4 would be 4 times 4,
this would be pi over 8. Not, or, oh no, yeah, you're squaring it.
so over 64 then, no?
No, it'd be pi over 16.
So we
Yeah,
use
pi over
25.
16. If you do pi over 16 times do to the, oh, I'm sorry, to the fourth, never mind.
So the 2 to the 4th. So it would
Yeah,
be
to the
2
fourth,
times
16
2,
times 4 is, yeah, 64, you're right.
64. So pi over
Remember that.
64. D to the outside to the 4th minus D to the inside to the 4th. Okay? So at the end, the bending stress is equal to, the expression will be M omega square, little r, capital R, outside diameter divided by 2, divided by pi over 64, d outside to the 4th minus d inside to the 4th. So any question? Okay, so here this is just a general question, okay, general design question. Is it a good design to have a tube, so with an inside, instead of a shaft, solid shaft, to have a tube for bending?
No,
Where will be the stresses happening?
the greatest stress will always happen at the outside.
At the outside. So where do you want to have the material? At the outside, no? Does that make sense or no?
Yeah.
Where you have the
Yes,
stresses, we have the forces, you want to have the material there to resist it, no?
Mhm.
So really for bending, to have a tube is not that bad. Okay, there is another thing bad, it's not bad, it resists good, the stresses, a tube is really good. But what would be the bad thing about having a tube instead of a shaft? Is that it will have a twisting, the shear will produce a twisting, no? If it was some shear, okay? But for bending, what would be the equivalent if we were using a rectangular cross section? Every time you look under a truck, on the car, on a building, what do they use as cross section for beams?
Eyes usually.
I-beam. So why do they use I-beams? If you think about it, the tube is kind of equivalent to an I-beam, no? So why do they use I-beams?
Because along a certain axis, they're harder to bend
I mean, where do you want the material?
at the edges.
At the edges. So the I-beam is giving you the material to the edges, no? Okay? And it's not giving you much material in the middle. Basically just like the tube. Yeah? So basically they're kind of doing the same thing. So obviously something is not good for everything, no? If they're good for bending, they probably mean they're not going to be good for what?
Twisting.
Twisting, because we'll see. So if we need to plot the variation of the bending, what will be the variation? Will be 0 at the center of the tube, yeah? And it will be maximum at the other limit. Okay? All right. So now, let's go and see what will happen. So case 2, stress due to FC. So now, let me just do the figure again. So we have FZ will be going, let's say, in that direction, doesn't matter which one, okay, let's say FZ equal plus minus M omega square R, where this is Y X, Z. All right? So now, the force Z is creating a moment about what axis?
Y.
About Y. So we'll be creating a moment about this axis here. Okay? A moment about that axis. So now, if we transpose this one to point A, where is the cross section of point A? Circular over here. So basically, this is the Y. So really this moment here is creating what? A torque, no?
Mm-hmm.
Okay, and a torque in a cross section is inducing what?
Shear stress.
Is inducing then shear stress. Which the equation will be what? Then it will be, maybe you might remember that this form will be T C, let me call it C again instead of R, over what?
J.
J. So in this case, what will be T? T for us would be equal to what? Would be equal to Fc
Times R.
times R. So it would be same as before, plus minus M capital omega letter R capital R. What would be C?
Would be half of D outside again.
Yeah, same as before. And J will be,
Twice I.
no, should be half, no?
No, it'd be twice.
Should be twice, yeah. Should be, so it should be then pi over 32, the outside to the fourth minus the inside to the fourth. Basically what I'm saying is that J equal to I y plus IZ, no? That's the property we're using, okay? So it's half of this. So J equals to I, because on a circle, so J, the other way around. What did I do here?
Can you move the paper over a little, Professor? Thank you.
What did I do here? It was that way, the polymer of inertia.
Yeah.
Yeah, so it should be twice.
Mm-hmm.
Okay, so we're good, yeah. So the J should be twice, it was a 64, we multiply by 2 on top, no?
Mm-hmm.
We go over 32. Okay, so at the end, that means that the shear, the expression for the shear, will be equal to what? So, M, capital omega, letter R, R, the outside over 2, divided by over 32, the outside to the fourth minus the inside to the fourth. Okay, so did we get it? Do we have this problem right today? Clear?
Think so?
I think so as well. So I have a question for you about the J. So in here we know what is the J for a circular cross section. Do we know the J for a square or rectangular cross section?
Couldn't you just do IY plus IZ again?
Let me ask you a question. What is the physical meaning of the J or the I?
Oh, it's the resistance to that shape, or for the J, it's the resistance to that shape being turned about that the centroid.
Correct. So for bending, you think about it, If you do the I about this axis, would be the resistance for this cross-section to bend about this cross-section, no? If you do it in this direction, would be the resistance, I'm talking about bending now, resistance of this cross-section to bend about this axis, okay? If you do the same thing for the circular, that's why you know that it's the same for either one of the two. Now the J is what I say, is the resistance for the twisting, correct?
Mhm.
So in here, when you have something which is not circular, the fact that this over here, do you think the resistance, so what I want to say is that here the resistance to torsion will be uniform throughout the whole circle. With the resistance to resist the torque in that direction be the same everywhere in the cross-sectional area.
I don't think so.
You don't think so? So that's why if you look into any textbook, you're probably never going to find, or if you look on the internet, you're never going to find an expression that will give you the exact value for the J in torsion for a cross-section which is not circular. All right? If you want me to give you a more mathematical explanation, if you think about the I or the J, I know it's both of them, but what would be the J? Would be is something like x squared, I know it's x squared plus y squared, but it would be x squared over the volume. Okay? So basically what it looks is that what is the distribution or the mass, okay, of the mass of the object or the area from the center going on the x and the y direction at the same time. So a cross-section that is circular, you agree that the x and the y are going to vary at the same rate. Okay? But if you go to something which is not circular, the x and the y are not going to vary at the same rate. So there's really no way to find the J value for something which is not circular. Okay? So I just want to let you know that stuff that if you go to textbook and try to find the J for something not circular, you might find empirical expressions, but they will all be just approximations. Okay? So when you calculate shear for a cross-section which is not circular, what you're doing is a pretty rough approximation. Alright? So that's important on the conceptual point of view, because I will never do a design based on shear if the structure is not circular. Okay, you will just be guessing. Okay? Alright, so that's all I wanted to say about this. So 1, 2, 3, this is today. Today we are, let me put this here. I will put today. This is June 7th today.
Yes.
I need to scan all this stuff here. I will scan it today. Okay, so let's keep going. Yeah, I lost the pages before. It said this will be, oh, no page over here, no page over here, no page over here. Doesn't matter because that's front end. So page 75. We're going to start the chapter. So chapter 2, that would be 2. Yeah, I have 2 and multi-degree of freedom. Let's see, we can do multiple, but 2 and multi degree of freedom, which is called MDOF systems. Okay, so over here, I'm gonna start going a bit faster. I'm not gonna go to free vibration and then force vibration. I'm gonna go directly to the general case. So we're gonna look at force vibrations. So in this case, what we'll be doing, we'll be looking at two rigid bodies. So let's say they will be attached to the wall by spring K1. We'll have a damper C1. They will be attached between them with the spring, with the damper, and same thing on the other side, okay? You can have any variation of this system that you might think of, okay? Like not being attached to this side, not being attached to this side, whatever you want. So this will be M1, this will be M2. So this would be here X1, X2, and here we say this is going to be force vibration. So what do I need to add over here to be a force vibration?
Some kind of an arrow representing a forcing function?
And the arrow representing a friction function. Let's say it will be f of 1 of t. So I do the most general case that I can think of, f of 2 of t. Okay, so over here the free-body diagram, so the diagrams become a bit more complicated. So what is the procedure when you want to derive the equation of motion? You need to do a free-body diagram for each one of them, no?
Mm-hmm.
So if you want, we could do it that way. So yeah, let's do 2. I mean, I think it's easier we do. I think it's easier we do this way because you can see that then one faces the other one. Yeah, it doesn't matter, but okay. So let's say this will be M1 over here. This is M2, so this is moving really X1. This is really moving X2. All right, so here we need to be careful is really look at X1 and X2, okay? So now, if we start from this end, what force, and assume everything is moving to the right, okay?
Mm-hmm.
So what would be the forces acting on M1?
K1, X1 to the left.
Would be the spring force here, K1, X1, and you will have the same thing for the damper,
Mm-hmm.
correct? Now you need to be careful. Now what's going to happen between at X2? X2 is connected to what?
Yeah, it's the
To M2.
So, would it be the...
So what is the spring doing the force? So we should have a K2, no?
Yeah, K2, then would it be X1 minus X2?
You can do either X1 minus X2 or generally people will do X2 minus X1.
Okay.
Okay, but it doesn't matter. So basically we say, if you assume that you pull it, okay, over here, you can do it the other way around. But if this goes in that direction, which way should it go then from 2?
Left.
On the opposite direction, no? Yeah?
Mm-hmm.
Now you can do the same thing here for the damper, with the damper. So it will be C2 x dot 2 minus x dot 1. Would be the same thing for 2. Then what will you have for K3? Remember, we're still assuming everything going to the right, so.
It would also be pointing left with K3. Would it just be x2?
Yeah, because this one is just connected to x2, no? x1, x2, or x2 minus 1 will be between both of them, so it will be x3, C3, x dot 3. Okay, and here I forgot, I still haven't put it, but what do I need to put over here now?
The forcing functions?
F1 of t, yes, and F2 of t. So if I go and write down the equation of motion for block M1, so we always do the same thing, summation of forces equals to MA. What will be the equation of motion for the block M1? If we look at the figure. What are the forces?
K1, x1.
Minus K1, x1, no?
Minus C1, x dot 1.
Minus C1, x dot 1.
Plus K2, x2 minus x1.
Plus K2, x2 minus x1.
Plus C2, x2 dot minus x1 dot.
Yeah, I mean, it's just a matter, the equations do not come out from magic, they come from figures, no? Figure diagram.
And plus
And that-
F1T.
Okay, plus, yeah, F1T, but then another space, and that should be equal to what?
MX1 double dot.
M1 X1 double dot. Okay? Okay, so now if I try to go and rearrange the notation here will be M1 X1 double dot. Then what will happen with C1? We have a C1 here, C1 here, no? So we have plus,
C1 plus C2 times x dot 1.
correct, C1 plus C2 x dot 1. Let's all do the x1, then what would be with K, what would be the x1s will be plus K2 x1, no?
Okay.
Would be K1 plus K2 x1.
Oh, K1, yes, K1 plus K2 x1. So we did this one, K1 plus K2 x1. Then what you're gonna have? Minus K2 x2, no, over here? Oh. What would be the best way to write this? It really doesn't matter, but I mean, let's finish to write down the equation. So M1, X1, C1, X2. So then we'll have what? We'll have a minus C2,
x2 dot.
X2 dot,
And minus
minus
K2 x2
K2, X2
equals F1 of t.
equal F1, yes. Okay, if we do something similar, for M2, So let's see what is M2. We look at the figure. Is this one over here? So what is the equation then? I mean, same as before, so we have what now? Minus K2, no? X2 minus X1 minus C2 X dot 2 minus X dot 1 minus K3 X3 minus C3 X3 plus F2 of T will be equal to what? M2 X double dot what?
2.
2. So this will be equal to what? M2 X double dot 2 plus
Plus C2 plus C3 X dot 2.
Yeah, plus C2 plus C3 X dot 2. I know what about here K3, this is 2. This is 2 and 2, yeah.
And then it'd be plus K2 plus K3 X2.
Plus K2 plus K3 X2, and then kind of similar to the one that we should have a minus, what? Minus
C2 X dot 1.
minus C2 X dot 1,
And minus K2 X1
X1
equals F2
equals
of
to
2.
F2. Can you look at the two equations here? Yeah. All right, so now what I'm trying to say is, or in matrix form, so I have you over here for the first time, so here we have the two equations. On the first matrix, we want to write down what is in function of x dot double dot 1, x dot double dot 2. So what should we have?
Would it be M1, M2?
Yeah, but so we have here m1. What should we have over here? On the first equation, do we have any x double dot 2?
No.
So this term should be
0.
0. Now, vice versa on the second one, do we have any term with x double dot 1?
No.
So this is 0. This is M2. Okay? Now, this time I'll let you do it, or let me know what is equal to. What would be the expression for x dot 1, x dot 2?
Would be, are we considering it 3 column or 2 column?
Here is 2, no?
No, I mean in the square brackets, are we calling it 3 column or 2 column?
No, it's 2 column.
Okay. So then you'd have C1 plus C2.
Okay.
And negative C2.
Here you have then, you need to look at the equation. which is this one here, so negative C2. Now if you look at the other one, what are you going to have?
Negative C2. And then C2 plus C3.
C2 plus C3. We do something similar for x1, x2. So what do you have for x1, x2? I don't know if you can see now, but
You'd have K1 plus K2.
it should be kind of similar to what you did with the damping, no? Yeah? So here what you're gonna have?
Minus K2.
Minus K2.
And then minus K2 in the next cell.
Yeah.
And K2 plus K3 in the last one.
And that should be equal to what?
F1, F2.
F1, F2. So this is the equation of motion for the two degree of freedom. Why is it called 2 degree of freedom?
Is it because there's two objects moving?
Because there is x1 and x2, no?
Okay.
Okay? So it can move in two different ways. So if you think about it, what could be the ways this could, physically what could be happening here? The two objects could be both moving to the right.
Mm-hmm.
Both objects could be moving to the left.
Yeah.
This one could be moving to the right, this one could be moving to the left. Or this one could be moving to the right, and this one would be moving to the left, no?
Mm-hmm.
Okay? So we need to be able to explain that physically. Okay? So now that we derive the equation for the force vibration, we're going to do the same thing as we did before. Before going and find the solution for the force vibration, we first need to go to find the solution for the free undamped vibration, no? And then we can extend the procedure. So let's take this one. All right, so let's over here. Let us first solve the undamped free vibration problem. If it's undamped, what does that mean?
C1, C2, C3 equals 0.
Yep. And if it's free,
F1, F2 equals 0.
L1, F2 equals 0. So if we substitute these values into the general equation, what do we get? The equation of motion will be M1, 0, 0, M2. X double dot 1, X double dot 2. plus K1 plus K2 K2 plus K3 minus K2 minus K2 x1 x2 equal to 0. How much time we have? Half an hour?
Yep.
There's no way we finish this. Okay, so now, so this is the equation for the free vibration problem. Okay, so, oops, what was the pages? What did I do with my first page? No, I did it, 76. Okay, 77. So what do you think will be the procedure to find the solution for the 2 degree of freedom? Should it be any different than what we did for the 1 degree of freedom?
Probably not. Start with assuming harmonic solution.
Correct. So we start with, so assuming harmonic solution. So it's of the form was x of t equal to capital X E. So if it's let's use here I lambda t, I use lambda, you will see why, okay? We could use omega sub n, it's the same thing. You want to use lambda or you want to use omega sub n?
Lambda's fine.
Okay. So now, so basically here, I mean, maybe I need to put it here. What if this is 1, then what does it mean? x1 equal to x1 ei 1 omega t, no? If this is 2, this is x2 equal x2 ei lambda sub 2 omega 2. Okay? So if you want, this would be equal to, or, let's put here, x1 of t will be equal to that x1 ei lambda 1 t. x2 of t will be equal to x2 ei lambda 2 t. So if we substitute into the equation of motion, okay, so what are you going to get if you derive once x1t? You're going to get x1 I lambda 1t exponential of I lambda 1t, no? If you differentiate twice, you're going to get minus x1 because I squared becomes negative, no? Lambda 1t exponential of minus lambda 1t. All right? So, if we keep the general notation as this one, what we're going to have is this. So I'm going to do this. So, ei lambda t okay, what will give you the m?
minus m1 lambda 1 or lambda squared.
Minus m1 lambda square. Yeah, it would be lambda 1 square, but let's just say lambda square. Okay?
And then 0 for the next cell.
0,
0 again.
0, and minus
m2 lambda squared.
m2 lambda square. And the case will give you what? Nothing will change, no?
Yeah.
So, I need to be careful here. I'm gonna write this down.
It would just be 1, 1.
Now maybe the previous way to write this down, but it would be x1, x2, no? Because this, all this one will be multiplied by x1, x2, x1, x2, no? So equal to 0, 0. Or I could rewrite this as being equal to what? Or, this is the way I wanted to write the first time. Ei lambda t minus m1 lambda square plus k1 plus k2 this one will be minus m2 lambda square plus k2 plus k3 Then what you're gonna have on these ones over here, you're gonna have,
Minus k.
yeah, minus
Two.
K2, minus K2. So basically, that equation over here is equivalent to what? See if I have here the last notes. See the equation of motion. All right, remember when we solved this problem for the 1 degree of freedom? Yeah? We did the free body diagram. We find the equation of motion. We assume the solution. We substitute it. And we found this equation, no? Which in mathematics is called the characteristic equation. Now, what do we need to do with this solution? With this equation? We needed to solve it, no? So we found one solution is when this coefficient is equal to 0, and the one would be when this is equal to 0, correct? So this is a quadratic equation which was giving us the two roots. All right? So basically here we follow exactly the same procedure. So now, when will this equation be satisfied?
If either e to the I lambda t is 0, or if everything in the curly braces is 0?
Correct. So the above equation is satisfied if ei lambda t equals 0, which is what we call the trivial solution. Okay? Or when all this term over here equal to 0. So over here, maybe, let me remove this over here. Let me remove this. Don't put it. I think I just confuse you. So when is this going to be equal to 0? Just use your common sense, okay?
When the top row and the bottom row are both equal to 0?
Almost. Basically, but think about this about like a vector or a matrix.
Oh, when all the components equal 0? No.
Okay, that will be
Yeah,
the
that's
trivial
trivial.
solution.
That's trivial, yeah.
But basically, I remember you could say that when the determinant of this will be equal to 0,
Yeah.
what is meaning the determinant is that this times this one minus this times this one will be equal to 0, no?
Mm-hmm.
Okay? So, let's put it here. The non-trivial solution is obtained when the determinant of that big stuff we just wrote down when the determinant of minus m1 lambda square plus k1 plus k2 minus k2 minus m2 lambda square plus k2 plus k3 equal to 0. Okay? So, let's go, if we do the algebra, what are we going to get over here? What do we need to do? We need to do this one times this one
Minus
this one times this one, no? We're going to get minus m1 lambda square plus k1 plus k2 times minus m2 lambda square plus k2 plus k3 minus what? Minus k2 minus k2, and this should be equal to 0. All right? Again, remember when we did the problem before for 1 degree of freedom, what did we get?
A quadratic equation?
Quadratic equation, no? So what do you think we're going to get now?
Some kind of polynomial?
Some type of polynomial, which probably is going to be a big quadratic equation. I mean, you can almost see it would be lambda squared times lambda squared, no?
Mm-hmm.
So we do now the algebra, what are you going to get? And we change colors, so we can do, it will be, the first step will be equal to what? We do this product, we're going to have m1 and 2 lambda to the fourth, no? Yeah?
Mm-hmm.
Then maybe can we combine them right away? Let's look now what would be the terms in lambda squared. So we have this one times this one. Yeah? So if we do now, let's say I do minus, I want to go a bit faster here. So what will be the terms in function of lambda squared? We have this term times this one. Correct? So that would be what? M1, we're doing this one times this one. M1, K2 plus K3. And then what would be the other one? Would be this one times this one. So plus M2, K1 plus K2. Anything else? No for lambda squared, no?
No.
And now we'll have some constant terms that will be the K1, K2 times K2, K3, no?
Yes.
Yeah? So plus over here, and I would write it, plus K1 plus K2 times K2 plus K3. And this one will give us what? Minus K2 squared. And all this should be equal to 0. Okay, so over here, what type of equation is this? That's a funny name, but I mean, it's.
It's a quartic?
I mean, if it was called a quadratic equation, we'll have lambda squared times lambda, no?
Mm-hmm.
So if this is called a big quadratic equation, wait a minute. Okay, or this could be what? A biquadratic equation. This is a big quadratic equation in function of lambda, or is what? A quadratic?
Equation in function of lambda squared.
Correct. Okay, so we're gonna go and solving the quadratic equation in lambda squared. Okay, so I don't know how to do this, maybe change a little bit. So what would be A? If we have the equation, like A lambda squared plus B lambda plus C equal to 0, what is A for us over here? M1 and 2, no?
Mhm.
What would be B?
The negative of M1 K2 plus K3 plus M2 K1.
Yeah, I could just put a minus here, but yes. Can I just put a minus here?
Okay.
What? Minus here. K2 plus K3. I'm trying to save some time. Plus M2 K1 plus K2. And what would be C?
K1 plus K2 times K2 plus K3 minus K2 squared.
Yeah. K1 plus K2. K2 plus K3 minus K2 squared. Okay, so the two roots of the quadratic equation will be what? Lambda 1 squared should be equal to what?
Nope, negative B plus or minus for the quadratic.
Let's say it would be plus. This would be what? B squared minus 4AC, no?
Over 2A.
Over to A. And lambda 2 squared would be minus B minus C squared minus 4AC divided by 2A. Okay. I'm going to say two more things. I'm going to stop here. The quantities lambda 1 square and lambda 2 square are known as the eigenvalues and they represent the natural frequencies of the system. Okay, so if you remember, what did we have on the assumed solution? I told you that we choose this, but I told you that you could use what?
You can split it up into 1 and 2.
Yeah, but that we could assume omega nt, no? Okay? Okay, so really what's happening here is that we ended up, at the end we ended up having what? A b quadratic equation for lambda, no? So really we're gonna have at the end that, so really should be lambda, but it's really lambda squared should be equal to omega n squared. Okay? So what I want you to know here is that eigenvalues equal natural frequency or natural frequencies. Okay, so have you solved the eigenvalue problem in all the math classes? Or this is the first time you hear that?
I've seen it in DPQ.
Yeah.
Okay, and when you solve the eigenvalue problem, what do you need to solve at the same time?
For eigenvectors also.
The eigenvectors. Do you remember what is the meaning of the eigenvalue or the eigenvector? What is the physical meaning? Or you only have a mathematical explanation? Okay, so this is why I'm stopping here because we're not going to have time, but what are we trying to solve in this problem here?
The position equations for the two blocks.
So correct. So basically, we have the two systems. Each one is going to have a natural frequency. Correct? We can go to the natural frequency. So now, depending on the natural frequency, what's going to happen? Either they're going to move, both of them are going to move at the same time. Correct? Well, the two types of motions we can have. Either they're going to move at the same time, doesn't matter if they move both at the right or both to the left, they will be moving together. Or the other option is that they are moving in opposite directions. Correct? So those are the two types of motions that we have. Okay? So how many eigenvalues we have?
Two.
Two. So probably one is going to correspond to what type of motion?
Unison and one to opposition.
Correct. One will be unison, the other one will be in opposition. So what is the mathematical stuff which is going to tell us if they move together or in opposite direction?
Initial conditions.
In this case would be the, well, I mean, you said before, we need to solve for the eigenvectors.
Okay.
Okay? So basically what we did is that, all right, we solved this equation here. That's why initially, we have this equation. So now, when can this be equal to 0? It's when this is equal to 0, or then this could be equal to 0, yeah? But then, depending on the value of x1, we have two values for lambda, no? In this equation, correct? So depending on the values of lambda, once we go and substitute here, it's going to give us different values for x1 and x2.
All right.
Correct? So when we look at those values for x1 and x2, if both of them, let's say x1 is positive and x2 is positive, will mean they move together. If one is opposite to the other one,
Then they'll move.
they
opposite.
move in opposite directions. Okay? So that's what we'll be doing next time. We'll be solving now. The last step we have to do now is to solve that equation here. Okay? We solve for x1 and x2 for one value of lambda. And then we solve for x1 and x2 for the second value of lambda. And we see what happens with x1 and x2. Okay?
All right.
So that we'll do that tomorrow. So you see that 2, the notation start being heavy. Imagine we start going to 3 or 4. So we don't do that by hand, okay?
All right.
All right, so see you tomorrow, no?
All right. See you tomorrow.